Right guys, I thought it was time to do another follow-up video. The last one we touched on pressure area and how that affects shim lift, and we're sort of going to carry on the theme on pressure and hysteresis and pressure balancing, and just talk about how the force is actually generated on the end of the shock shaft, and where it comes from and how the pressure influences this. So your shock is not much different than just a normal hydraulic cylinder, and that the force exerted on the end of the rod is the net force, and so that is the force acting on the top of the piston minus the force acting on the bottom of the piston. So much so that most guys, when they run a shock up on a dyno, the first thing they'll work out is the gas force. So they'll compress the shock shaft a certain distance, and then work out the force that's been exerted on the end of it, and that's usually the sum of the gas pressure times the area of the piston minus the area at the bottom. So it's the net force, the difference between the force at the top and the force at the bottom, and so that's very much like a hydraulic cylinder. And so we're going to talk about how that force is generated, or how the pressure is generated and how that influences the force. So over here we can see we've got some numbers. So this is just for this 50 mil WP shock with the 80 mil shock shaft. So we've just worked out the areas. So area of the top of the piston is 1962.5 millimeters squared, and then obviously with the 80 mil shock shaft, so the area at the area of the bottom of the piston that's occupied by the shock shaft is 254.34 millimeters squared. So that leaves an effective area of 1,708 millimeters squared. So we're going to talk about this pressure differential and how that can be accumulated, and look at two different examples here. So first off, we have something similar to what a KYB would operate like. And we've got 500 psi in the compression chamber with 220 psi in the rebound. So we can just use a simple app online. Force equals pressure times area. So it's 689.88 minus 264.21 equals a net force of 425.6 kg. So now we're going to look at a second example, and we've got the same force number but generated in a different fashion. So in this example we've got 650 psi in the compression chamber and 392 psi in the rebound chamber. So that's going to give us 896.85 minus 471.18. Now the thing to note here is that these two shocks, although they would generate the same net force, they would ride very different. Coming back to this hysteresis and pressure balancing, we can see here that example 2 has 78% more pressure in the rebound chamber. So when it comes to that transition between compression and rebound, it's going to take a little while to dissipate that residual pressure, that extra pressure that's in the rebound chamber before it starts to rebound stroke. And that's that whole hysteresis, the whole delay, the transition at the rebound stroke. So we're going to move on. We're going to look at some real numbers. So for anyone that's really keen on learning stuff, I suggest you sign up to Valving Logic. It's a very useful tool. Very nice guy. He does some proper dyno runs, pressure traces. He's got a whole lot of information on there that's very helpful. So look it up, valvinglogic.com. But here we have a YZF shock. He's measured on the dyno. He's got his chamber pressures, compression and rebound chamber pressures, which you can see here. The first number for force is pounds, and then I've converted it to kgs. And we can just do, again, we can use the app, and we can just do the difference between the force acting on the top versus the force acting on the bottom. And if we do it like that, we just come up with these numbers here, which you can see within 4 to 6% of the actual numbers. So it's very much how it works. It's very similar to just a hydraulic cylinder. So now we're going to touch on how that force is generated and how you can influence the pressure build-up inside the damper. So next thing I want to look at, so I did some pressure tracing a little while ago now, it's probably about a year ago. So we just made this little contraption over here. It's real simple. This is just the vessel to hold the piston assembly in, and you can see here I have just this contraption. So I'll put the phone down for a second. So here we just have the piston. It's just on a pedestal, and what we did is we put it in this capsule, and we just ran oil through it, and we just measured the pressure drop across it and recorded the flow relative to the pressure drop. So here's the numbers. And so what I did, I just wanted to keep it really simple, so I just had a straight tapered stack. I had essentially 20 times 0.20 shims clamped on a 23mm shim, and I ran the test, and then I just added 2 face shims, so basically added 10% more shims, and interestingly enough we just got a 10% reduction in flow for the same pressure drop. So that's the thing you need to keep in mind. It's not overly complicated. If you add shims, you'll get less flow for the same pressure drop, or you'll get more pressure drop for the same flow. Either way, it's the same thing, so just said in a different fashion. So here you can see, obviously this is where the shims start to crack open. We start to get some decent flow, but you can see here that the difference was approximately 10% for 10% more shims on the piston. So that's the thing with the piston when they work on their own, so independently. But obviously what we've got going on in a shock, and we've talked about it before, is we actually have 2 pistons. We have our main one, and we obviously have the compression adjuster as well, which is to flow the volume of oil that needs to be displaced to allow room for the shock shaft to come in. So we're going to touch on that in a second. We'll come back in a minute. I'm just going to put up on the screen, I'm going to put some flow charts from an actual study, so you can just see what that looks like. So again, it's just the same thing. It's going to be the greater the pressure drop, the greater the flow, much like what we saw here. So as the pressure drop increases, the flow increases. So we'll come back in a second. Okay, hopefully you could see those pressure drop diagrams from that study. I'm going to share the link to it in the comments, that and another one as well, which are both very useful. So hopefully you'll get access to those. But I'm just, obviously I've done those proper pressure tests, but we're just going to draw a real simple diagram so I can explain it a little bit clearer. So obviously over here we have pressure drop and we have flow, and this doesn't matter, whichever valve we're talking about, they work on the same principle, and that is that if you stiffen the stack, you'll reduce the flow at the same pressure drop, or you'll need more pressure drop to equal the same flow. So we can see it over here, less flow at same pressure drop, more pressure drop at same flow. And the thing to keep in mind is flow is relative to velocity, and pressure drop is essentially our force. So when you start to think about it like that, it all starts to make a bit more sense. But what I really want to talk about is obviously with this whole pressure balancing and how that pressure is accumulated in the chambers. And obviously I think the topic of contention seems to be this compression adjuster, or in the case of the forks, the base valve, and how that influences the pressure, and how changing the main piston influences the pressure. So as you can imagine, we set our shim stack, whatever that might be, and we've dictated our flow through the compression adjuster relative to the pressure drop. So people will say, well, that's the force that's been generated across the compression adjuster. But the thing is, although the compression adjuster contributes to the pressure inside this compression chamber, it doesn't actually mechanically apply any force to the shock shaft. The force that's applied to the shock shaft is the pressure acting on the top of the main piston, minus the pressure acting on the bottom of the main piston. Nothing more, nothing less really. So this compression adjuster can set the tone for the pressure inside the compression chamber, but it doesn't actually apply any direct force to the damper rod. So we've set a stack and we've set our flow rate through here. Now what happens when we change the shim stack on here? There'll be a lot of guys and they've got dynos and they've done some pressure tracing, and they say, well, when we change the stack here, we see a greater pressure drop. We see more force, which of course equals more force, because now we have less pressure underneath, so less force on the bottom side of the piston. And they're saying, but we're not seeing any significant increase in pressure in here, so it's having no impact on the compression adjuster. But the thing you need to remember is we've set the flow on the compression adjuster, so that flow, as the pressure is now generated quicker in the compression chamber, all that excess pressure is being bled off, because this only maintains a set pressure. It's like a pressure regulator valve. So as you accumulate more force in here, more pressure in here, it's bled through there. So that's where people get a little bit confused. You'll speed up the flow, because obviously the flow is set by this pressure drop. So if we start to increase the pressure drop, we increase the flow. So you'll never see a significant rise in pressure. No matter what you do to this, you'll never see a significant rise in pressure at the same velocity in this compression chamber, because you've increased the flow across here. And that's how that whole hysteresis works, is that, when we get all this misbalance, we start to get imbalance in the flow between each valve, and that causes all those delays with those residual pressures. So I think sometimes people want it to be a little bit more complicated than it is. Maybe I don't know why they might want to do that, but it's basically you set the flow with your shim stack stiffness, and it's just going to determine how those shims pull away from that piston. So that's it's definitely something we've got to keep in mind. So knowing that basically the flow across the valve is just relative to the pressure drop, and which is all relative to the stiffness of the stack. How does this influence this pressure? Like example 2 that we saw earlier on, with the higher pressures in the compression and rebound chamber. Why would we see that? What causes the shock to do that? And in this case, WP's particularly prone to it because of the setup on the compression adjuster here. So when you have what's essentially a stiff compression adjuster, and that doesn't need to be stiff in the shim stack. In this case, I believe WP's main issue is the design of the piston, which I explained in the last video. So there's a massive delay in how the piston opens, because obviously it only had a third of the area of, say, a KYB or a shower shock. So obviously there's that massive delay, and then unfortunately once it does open, it just swings open, and you get all these flow imbalances. So but if you took one shock and you just started beefing up the compression adjuster stack, what will essentially happen is, because we increase that graph, the gradient of that graph, so we start to really steepen it up. In this case, we go real stiff like that. That means we'll start to see higher pressures, because we require a higher pressure drop. So we slow down the flow here. We have the shock shaft coming in, and the shock shaft coming in, it needs that space in the rebound chamber, but unfortunately we haven't evacuated enough oil through the compression adjuster. So then we just start to see, as the shock tries to compress everything, we start to see these higher pressures, and that's clearly what Penske talk about on their paper when they say excessively stiff head valve. You just generate excessive pressures. So the whole idea of tuning a damper is to produce as much force as you can, or you require, as much force as you require, with as little pressure as you can, because that way when it transitions at that compression to rebound stroke, there's less residual pressure in the damper. So the most effective method of doing that is by generating more pressure drop across this main piston, utilizing our gas pressure to obviously not getting any cavitation. So in this case, most shocks are operating at 150 psi. So we can run this if we needed to. We can run this rebound chamber down to 50 psi, 100 psi by having a decent shim stack on the main piston. Means we're going to see a bigger difference in pressure across this main piston, which is going to result in a higher net force without all that excessive residual pressure. So that's the thing. So we just want to tune this so it's like there's that balance between these two valves. Obviously this is only flying such a small portion of oil, as we discussed in the early videos, whether it's the shock or KYB, we're talking about 30 odd millimeters versus 240 millimeters going through the main piston. So this is flying the most oil, so obviously this should be doing the most work. So yeah, if you're really keen on tuning dampers, I think it's keep it simple to start with. Don't get caught up in there's a lot of gimmicks out there and a lot of false claims. Just keep it simple, keep the straight tapered stacks, just simply add and remove stacks to try and get this balance going. Look at what KYB does. I mean, it's $1 billion company. By comparison, it's like about 50 times bigger than WP. Been around for a long time, making aircraft landing gear before most of us were born. So they're definitely who I tend to follow. I follow their lead. Plenty of research papers out there, so look for those. I think your best bet is to move away from the moto industry for a while and look at what the automotive guys are doing, maybe what the road race guys are doing. They're all some pretty clever guys, and obviously larger industry than motocross, so there's a lot more research and development going into that. But that's going to be it for now. I'm going to come back with one more, I think, and I'm just going to go through a change I did recently on a shock for a guy. He had it tuned somewhere else, wasn't quite happy with it. We had one crack at it and got it right on the money by keeping it simple. So I'm going to show those numbers and explain why I did what I did, and go from there. All the best.